Okay, shall I just zoom in maybe?
Sure.
Um, all right, is that any better? Okay, so if you have a lens of some aperture diameter and then it's got a focal length, then the F number is the ratio of those two. It's the focal length divided by the aperture. So it's how you talk about the aperture, but it's an upside down measure of it. So that's where a lens, a typical camera lens might be f2 and has a aperture of 25 millimeters, a focal length of 50 millimeters, something like that. So that's what the 2 refers to. It's the focal length divided by the aperture. Now he says if you've got a really fast lens, it might have an F number of 0.8. I've never seen anything that fast. But apparently such things are possible, at least. So to have a number that small, you'd have to have a much larger aperture. And so you can imagine designing the lens would be harder to be able to converge rays from that far out and still make a perfect spot here. But that tells us then the relationship between the focal length and the diameter. It's related by this 0.8 number. But we don't know either one. We just know that that's what the ratio is. So then just looking at diffraction effects, this is our sort of well, yeah. The basic resolution formula is, this is the Rayleigh criterion right here, is that the angle between 2 points that you can just barely resolve is 1.22 lambda over d. I'm not sure why I put this formula in here. It's not, it's sort of the basis, I guess, of the Rayleigh criterion. But the Rayleigh criterion is really all you need. This would be an angular distance between 2 points. How far apart are they separated in angles? So up here, you would imagine here's 1 point, and now you want to be able to distinguish that from some other point over here where different rays are converging to form a spot over here. How far apart in angle are those two? That's the angle that comes into the Rayleigh criterion. And now what I do is just put in, instead of D, I put in this F over 0.8. And if you do that, then you get the angular size of the spot. But the actual physical size of it, in other words, how far apart are these 2 points, that depends on the angle and the distance. But in the simplest possible way, it's just the angle times the distance. As long as you do your angle in radians, you can approximate it that way. So that's why I just take the angle times the distance. The distance is just the focal length. So the focal length cancels out of the whole thing. And what's more, if you're using Rayleigh criterion 1.22, and then a size of the lens is 0.8, you end up with just 1 for this thing. This 0.8 is in the denominator of the denominator, so it's really up on top. And 1.22 times 0.8 is basically 1. So what we find is the size, the smallest size of features we can discriminate is whatever the wavelength of light we're using. And that's the rule of thumb everybody uses when you talk about what's the tiniest thing that you can see with an optical microscope. It's basically the wavelength of light. I don't know if that's the, I don't know, clearest way through this, but the point is the focal length ends up canceling out. And the aperture just depends, just because if you have a fast lens, it's the aperture is just a function of the focal length, and so it all cancels out.
We were trying to like make up numbers for the focal length, so we just used a focal length of 1 for ease.
Mm-hmm.
But I think we were missing the part about getting the focal lengths to cancel out the theta f.
Yeah. Well, did you have this 0.8? Did you have that as a ratio?
Yeah.
Okay.
Yeah.
Well, then it should have come out. Shouldn't have mattered what number you put in for that.
Well, we were forgetting to multiply by our focal length at the end.
Oh, down here.
Yeah.
Right. Okay, other questions on that? I'm curious how you did on 28. This lovely picture.
One by 3, right? 1 slit per 3 slits.
Yeah, that's right. And what about the dimensions of the individual slits? Did you not work that out?
They look to be about a third as thick as the distance apart.
Yeah, I would have said a factor of 2, but we can quibble about that if you want. You're looking for where the envelope is heading down to 0. And I would have said it's up here at a peak and it's heading down. It's already halfway down. I figure, okay, it's going to get down to 0 right about at the next one. And counting these, that's 0, 1, 2.
Okay.
It's the factor of 2. That's what I would have said, but it's a guess. It's something of an estimate at that point.
So the distance between the slits is twice as wide as the slits are, or the slits are twice as.
Being careful to say not exactly distance between, but center to center is twice the individual slit, which means ultimately you have the slits are some distance x and the opaque parts between them are that same size. What about the other dimension? Can we figure out how long the slits are? You can actually from this. Where is the first minimum in the other direction of the single slit pattern?
About the same distance away as the first minimum on the other direction?
First minimum on the other direction from the single slit is way out here, out at the very edge. But in the other direction, it's just a single slit pattern and it's pretty condensed. It's coming right down to 0. This is the first sort of ghost and the next one and so on. Those are not multiple slit effects. That's the single slit effect. So the first minimum is right there. That's much closer than it was out here. Now you have to work out, I don't know, ratios here somehow. I decided it was about 5 to 1, but you have to decide, you know, how much is that distance compared to that distance out there. So if that's 1, 2, 3, 4, 5, that's how I counted it. But that's kind of an estimate. Going from the middle to that point, comparing that to the middle all the way out here, assuming that that is the same as this, assuming this thing was really square. So that gets you the length of the slits, the length along this dimension, essentially. So I end up deciding we've got a set of slits that looks like that. So along this direction, we've got 3 slits, and their width is well, their separation is twice their individual width. And then the other dimension is twice these individual ones. No, not 5 times the individual. So the rectangle is a 1 to 5.
And what does the fact that we only see one full iteration of the triple slit pattern underneath the envelope of the single slit pattern, what does that inform us about?
I'm not quite sure what you mean. You mean the fact that we don't see the ghosts out here of the single slit pattern? Is that what you mean?
So if there were more iterations of the triple slit pattern before we got all the way down to that minimum, that would tell us how, that would talk about the ratio of the width of the slit to the distance between this distance from center to center.
That's exactly right. Yeah.
Okay.
That's exactly right.
Okay.
Yeah. Yeah, here's another picture I sort of drew to say we're seeing big peak, little peak, big peak, little peak. These little ones are probably too large, but and then the dotted line is sort of the overall envelope, and it's coming down to a 0 out about where the this would be 0, 1, and somewhere about 2 out here is where I would see that one. And you're saying, well, if we had more of those in here, then you could have a ratio of 1 to 3 or something like that, or 1 to 4. Yeah. Okay. That was 28. And we just did 38. What else did you want to look at?
Can we just see the answers for 46 real quick to make sure we got the right numbers?
Sure. So yeah, 50 meters is what I got. So you're not going to be able to see anything. And then for the eye, I get 63 kilometers. Okay. Does that match with what you were finding? Oh my, 72. That's a hard one. But it's kind of where we are. Shall we look at it? I'll give you the numbers here. So here was my calculation of the zone radii. R1 was 1.73, and then they all just scale after that by the square root of n. Is that what you folks got, or didn't you? Weren't you able to get that?
What was the original question actually asking? We got m equals 3.
Well, n equals 3 is what peeks through. Yes, that's correct. Let's see, 72. Let me find it.
And how would we be able to tell whether a zone is going to be bright or dark?
Yeah, okay. The first question is, how many Fresnel zones will be seen? And you got n equals 3. If you look down this list, you'll see n equals 3 has a diameter of 3 millimeters, a radius of 3 millimeters, and that's exactly the size of the hole. So there you are. That's the 3 answer. That's the answer to the first part. Now, will that point be bright or dark? So right at the center, will that be a bright point or a dark point? And that requires looking at these kinds of figures. Here is that very situation. That's looking at the very center, looking back toward the aperture, and then sort of superimposing on the aperture those Fresnel zones. And you would have 1, 2, and 3 zones fully visible and nothing else. Remembering that those are half wavelength or half cycle zones, 1 and 2 are right out of phase with each other, and they have the same area, so they're going to cancel out perfectly, leaving zone 3 to come through. And so you'd expect it to be bright because you've got 2 odd zones and 1 even zone would be one way to say it. It's not balanced. They don't cancel.
So then the dark zones we just assume are illuminated?
Bright and dark here are not meaning what you're thinking, I don't believe. The bright and dark are just different colors or different ways of sort of shading to tell which zone is which. And the zones just represent different phases. Light is coming through the whole aperture. And the light in zone 1 is of a certain phase, and of zone 2 is shifted by half a wavelength from that, so it's out of phase. Zone 3 is shifted a whole wavelength. So 1 and 3 are in phase, and 2 is out of phase with that. That's the idea. Now, in fact, this is kind of a crude model. It gets you sort of the right ideas, but in fact, the phase varies continuously. It's not, you know, these discrete changes, but we just sort of ignore that. It gets you mostly the right answers, and so that's how you analyze things. You can make a zone plate, Ben, that does in fact where you decide, okay, I'm going to allow only the odd zones through, and I'll make the even zones opaque. That's making a zone plate of some kind. But this is just a simple aperture. And we're using this zone method to try to figure out where is bright and where is dark.
So when we are saying bright and dark, we don't literally mean like there won't be light. We just mean it will be darker. Like, I guess the question is, what exactly does bright and dark mean?
Well, okay. For starters, this point, clearly there will be some light coming through because we have 1 and 2 canceling and 3 not. Mm-hmm. So because of 3, there's going to be some light coming through. And the question is, as you shift the aperture, can we imagine getting to a point where there's none? And that's a little hard to argue for. I think you can. Go ahead.
If we had it lined up so just zones 1 and 2 were visible,
yeah,
there would not be any light coming through, or we would not perceive any light coming through?
That's correct. That would be a complete null. There'd be nothing there.
Okay.
Yeah. Now, as
But
I
if
shift,
there
okay,
if there's an odd number, there has to be visible light because all of the evens cancel out with the odds and there's one odd left over.
exactly,
Okay.
exactly.
Sorry,
Yeah.
continue.
So what I've got then is a bright spot here right at the center. That corresponds to this figure over here. So A and A. And then what I did was imagine shifting this over and starting to get a little bit of zone 4. And losing on this side a little bit of zone 3. So that's pushing things back more into balance. And when you get to this one, you've lost quite a bit of zone 3, and you've gained quite a good deal of zone 4. Where does that leave you? I don't know. It's hard for me to see what you would call that. But it seems like that is the position where we've reached the worst spot in the sense of getting less and less of the light that we had from here. We've lost a lot of zone 3, and we've gained a good deal of zone 4. So are we now at a point where the zones 3 and 4 are going to cancel? Probably not. It looks to me like zone 3 is still, there's still more of it there than zone 4. So this probably still isn't, and it's not even clear that this is the worst spot. But as we go beyond this point, then you start catching a little bit of zone 5, and you start losing a bit of zone 2. So that suggests you might be going back the other way again. The logic gets less and less clear the further you go down these diagrams of exactly what's happening and is it going up or down. It's quite clear from A, you've got a maximum and you're going down. It seems not too far-fetched to say C is probably a minimum. And after that, I don't think you could make much of a very clear argument. But I went ahead and called E a position that looks like a maximum, but I think that's a little bit unclear. So that just represents kind of walking off in one direction. In actual fact, the figure that you're drawing is going to be a two-dimensional one. So it'll have a maximum at the center, some kind of a minimum. It's going to have rings going around like this. So that's what I was attempting to draw down below here. Except that the dark pencil represents brightness. Yeah, does that kind of make sense? These are not easy to reason through. I have to sort of study this again every time I go through this and try to understand it. Okay, well, for even more confusion, should we go on and look at 90?
Can we check your answer for 73?
Oh, 73. Yes, we sure can. Here's what I got. 1.5 millimeters. Do you agree with that? Yeah, great. Okay.
We got 1.53 millimeters.
Oh my.
Keeping our significant digits.
I guess so. I think I would have 1.56. I'm just seeing a 0.753 here.
possible I just made a
No,
mistake.
I would have a 1.506, I think.
Oh, maybe that was supposed to be a 1. Maybe I have 1.51. In any case, we got the same answer.
Yeah, 1.506 is what I would have here. I can be certain that there's a 0 here. Well, except you call it a 1. It should be rounded up to a 1, I guess, shouldn't it? All right. We'll carry one more digit. What are we given? We're given a wavelength to 5 digits of precision. Although we've taken a square root. I've forgotten, does that improve it? I think it does. I think you get more digits of precision, so we could probably quote the answer with maybe 6 digits or something. I don't know. Okay. That was 73. Oh, and 90 is on the same page. 90 is hard. So what you get is something that looks like this. If you've got a slit that's very wide, then way out at the edges, it just comes up from no intensity and smoothly comes up to a peak and then wiggles. And then you go through wiggles on the way down again as well. But out past the slit, there's nothing going on. There's no wiggling going on out here. It's just on the bright side of the division that you get the lines. Now, trying to understand that is just plain hard. So if this is a really wide slit, you have to imagine that then W or delta W is large. Trying to find where I've got this Cornu spiral. Here's the spiral. I want to show you this one here. So this is trying to show you where you've got a slit of some width, and the width ultimately becomes this parameter that goes, that you plot along the curve. And then if you're sitting right in the center, that's what this diagram would be for. And the intensity would be this phasor vector that goes from one end to the other. So that's a strong intensity. And then as you migrate from the center, you shift the ends of this curve. And now it starts getting weaker, but as this goes up here, the other end is going to start wrapping around here, and it might oscillate a couple of times before it swallows up the second one. Do you see what I mean by that? As you drive this in here, the right end, the B2 end, is going to go around a couple of times before the B1 end comes up into the spiral. And while that's happening, the length of this vector is going to oscillate. That's the oscillation you get. Then when it gets into there, then it just starts getting less and less intense as you get further and further away. It's just according to however many times it goes around in there. This is weird. And maybe this is out of date. I'm just thinking, does anybody care? This is a graphical way of thinking about what's going on. And we don't use graphical methods so much anymore. It's supposed to give you intuition. Maybe it doesn't succeed at that. I don't know. but that's what you're supposed to be seeing. And if you had a much longer slit, then this whole thing is just wider. And now as you shift, one side will be oscillating longer before it sort of swallows up the other. So the whole figure gets wider. So you end up with something like this, and as you make the slit wider and wider, this whole thing separates. Something like that. Well, I don't know if we're going to be able to resolve that one. You guys are sort of looking at it and half understanding it, I think, is where we are.
And this is for rectangular slits?
Exactly. Yeah.
Okay.
And you do a figure like that for each dimension.
Okay.
They're essentially independent.
Is there an easy way without doing tons of calculus to figure out what's going to go on numerically, or should we just kind of go with what seems right graphically?
Well, you can use the, oh, where do we have that? You can use the Fresnel integrals to calculate it directly. And that's what the whole Cornu spiral was based on. That's these two, the C of W and the S of W. And remember, W is just either U or V. And U and V are rescaled X and Y. So you use this to find out what's the intensity along X and Y. And it's just these kind of weird integrals that you're carrying out. Oh, where is the weirdness in them? I've forgotten now. Yeah, he doesn't actually graph them. Well, yeah, he does. Here we are. These are the two functions. And like I say, if you happen to have some kind of package that has those already calculated for you or can calculate them, then you can get these answers directly. You don't have to go through the graphical method at all. You can just calculate it and see what the answer is. Something's wrong here. Yeah. That's basically right. I don't like the curve down here. It looks to me like a draftsperson used a little curve here and then made it straight. But it isn't a calculated curve, I don't think. Anyhow, that sort of curve enables you to explain pictures that look like this. This is the kind of thing you might get with some kind of square aperture of different sizes. And you wonder, where in the world are all these stupid fringes coming from? And that's just what happens. Yeah, these are all just square apertures. Yeah. So there you go. That's all about square things. But I'm not going to expect you to try to do that sort of thing mathematically at all on the final exam. So what about those those two, what were they, Fourier series. I was just realizing I hadn't done the one, so I don't have the answer. I know kind of roughly what it is, but I don't know in detail. Did you get to those?
It would be good if we could go over them.
All right.
That was, at least for me, something that I didn't ever quite fully understand, I don't think.
Try the first one, which is what I was working on and didn't get done. So this is back in chapter 7. What were the numbers again? Oh, 52 was that one?
I thought it was like 44 and 45 or something like that.
It's 52 and 53.
52 and 53, okay. Let's do 752. So it says that the function we're trying to get the Fourier transform of is defined by sine of kx for x between, well, kx between 0 and pi, and 0 from pi up to 2 pi. And I would always suggest you make a graph of your function when you're doing this kind of thing. And so this is a sine function up to the value of pi. And then after that, it's exactly 0. So this would look something like that. That's our function. This would be f of x. And down here, I'm graphing apparently kx. Guess I could call it kx over here. So now if you remember your Fourier transform, the idea is that you can write f of x as a0 over 2 plus then a sum of other a's, a sub m cosine of mkx, where m goes from 1 up to infinity, plus also a series of b sub m times sine of mkx, where this also goes from m equals 1 to infinity. The only question is, how do we figure out what these coefficients are? What the...
Do we not have a b sub 0 anywhere? Or
there is not. No, there's an
okay.
a0, but there's not a b0.
Okay.
Yeah. So then we're told that the way you find these different a's is that a sub m and this is using Hecht's way of writing it. Every book has their own way. Well, actually, you normally would integrate from 0 to lambda. I'm already putting in lambda over 2 because there's no need to integrate beyond this point. There's nothing there. We're going to get a 0 because in a little bit we're going to be multiplying by the function. So what you do is it's supposed to be f of x times the very term that we're getting the coefficient for, cosine of m kx dx. So for each of these Fourier components, we multiply the sort of function by the original function we're trying to get. So to figure out how much of a particular, so for example, let's just look at m equals 1. And so here's m equals 1. That means we're looking at cosine of kx. Where up here was the function was sine kx, now we're doing cosine. So this is the Fourier component. And we're trying to figure out how much of this is present in that. And what you're doing is multiplying these two together and then integrating. I think you can see when you multiply these two together that everything's going to cancel out. You're going to get exactly the same amount here as you do here, except for a minus sign. There's a sort of symmetry here. And so it's going to cancel out and you're going to get 0. So A1 is clearly 0. What about for m equals 2? Then we've got a cosine of twice that frequency, I guess we could say. So that's going to look more like this. Now I can't make that argument anymore. If I try to split this thing up, the negative parts are in the middle. The positive parts are at the edges. We'll probably get something. We would not expect that to be 0. We could ignore the stuff from here on, but even within this, when we multiply these two functions together, we're likely to end up with something. Similarly, for m equals 0, we should get something. That's just the integral of this thing, times 1. And because the cosine of 0 is just 1. Does that make sense? So for m equals 0, we're going to get something. For m equals 2, we're going to get something. It's not too much of a stretch to guess that m equals 3 is 0 and m equals 4 will get something again, and so on up the line, that we're going to get only even results for the cosine coefficient, the a. Shall we do those? I think maybe we should. Let's actually do the integral. So writing this out in more detail is going to be 2 over lambda, integral from 0 up to lambda over 2. F of x now is going to be sine of kx times cosine of mkx dx. 2 over lambda. Now here is where I pulled out trig functions. I don't know, you guys probably just plug it in at that point and be done with it.
Can you move the paper up?
Yeah.
Thank you.
I gotta find my trigonometric formulas. So the formula I've got here is that sine alpha cosine beta is 1/2 sine of the sum alpha plus beta plus 1/2 sine of the difference alpha minus beta. So this is going to be the integral up to lambda over 2, and now it becomes 1/2 sine. You know, let's ditch the 1/2s. We can swallow those up out here and just say 1 over lambda. And now we don't have to say 1/2 at all. We can just say sine of alpha plus beta. That would be kx plus mkx. That can be written more easily. Kx plus mkx. That's just going to be m plus 1 times kx. Actually, I should write it as 1 plus m, just to be more clear. 1 plus m times kx. And then we have a second sine term, and this time it's 1 minus m times kx. All of that dx. Now it's time to take the derivative. Not the derivative, to do the integral. Sine becomes minus cosine. Cosine of 1 minus m.
John, shouldn't you also take the derivative of what's inside the cosine or the sine
Yeah, I haven't done
function?
that yet. You're
Okay.
exactly right. I just haven't done that part yet. I have to divide then by,
1 plus m over k
this would be 1 plus m times k, and over here would be 1 minus m times k. And then evaluate all of that, where x goes from 0 to lambda over 2. Which is kind of a dumb way of saying it. What is lambda over 2 in terms of k? Lambda is 2 pi over k. Lambda over 2 is pi over k. So we could say x goes up to pi over k. So 1 over lambda minus cosine of 1 plus m times pi over k times k is just pi divided by 1 plus m times k. One minus m times pi divided by 1 minus m times k. Oops, I'm not done yet. It's that minus the value at 0. So at 0, I think this is just plus 1 plus 1. 1, oh, well, okay, still got to divide. The cosines are just 1 at 0. So it would be 1 divided by 1 plus m times k plus 1 minus m times k. Getting off my page here. I think what I would do is put these two together and those two together. Cosine of 1 plus m times pi.
Wouldn't it be 1 minus that quantity?
1 minus, yes, exactly. Divided by 1 plus m times k. And then over here would be 1 minus the cosine of 1 minus m pi. All of this divided by 1 minus m times k. And this is with a 1 over lambda out here, which will get rid of this k that's inside. It's easy to get lost in the weeds at about this point. What we're trying to, in a sense, we're doing this for all different values of m. And what we might hope to show, and this is why I do these pictures up here, is to see roughly what do I expect to get. So what I'm hoping is to be able to show that for odd values of m, we should get 0. Can we see that? If m is odd, then this is going to be cosine of an even number of pi. An even number of pi, that's going to be 1. 1 minus 1 is 0. And the same thing is true over here. 1 minus m is still an even number of pi's if m is odd. So for all odd m, a sub m is 0. We can see that right now. For even values of m, then this would be -1. So for even m, we would have 1 over lambda times 1 minus a -1 divided by 1 plus m times k plus 1 minus a -1 divided by 1 minus m times k. So we've got 2 over lambda times k, which I think is pi. What is that? Lambda is 2 pi over k. I think that's 1 over pi. And then inside here, what's left, I pulled the k out. We're going to have 2 over 1 plus m plus 2 over 1 minus m. And then you have to figure out how would you simplify that. Take the 2 out, 2 over pi, and put it over 1 plus m times 1 minus m. Does this get any simpler? I'm not sure. So this would be 1 minus m plus 1 plus m.
That would be 2 over that quantity then?
Yeah. Did we help ourselves any? 1 minus m over 1 plus m. So this is 2 over pi. And in here, this is now a 1. No, it's not. I need to put a 4 out in front. It's 4 over pi now. That takes care of the 2 in here. And I've got 1 on top. Can I write this as 1 minus m squared? Difference of perfect squares. Hey, there we go. I think we're done with...
How did you get an extra 2 out in front?
Because 1 plus 1 is 2. The 2's here.
Oh, okay.
These 2 1s add together to make another.
Oh, the
2.
m's just cancel out. I see.
M's cancel,
Yeah.
the 1s survive.
Yep.
That's not too bad an expression. That's what you kind of hope to boil it down to, something like that. So as m gets larger and larger, the coefficients get smaller and smaller, and that's what typically happens. And it happens as a kind of m squared in this case. So this is for the even values of m, which would include 0. I think this still should work for 0. It suggests that the A0 level is just 4 over pi. A0 coefficient would be 4 over pi, and the other ones would be different values. Now, we're still only half done. You have to go back through and find the b's, which you get by a similar integral, but it's got a sine function in here.
You think we could take like a 10-minute break to get up and do stuff for a little bit and then come back to this?
Sure. You need a bathroom break or whatever?
Yeah, just a stand up and stretch break
Okay.
right now.
All right, let's do it. I'm nearly done. I would like to look at one more.
really hope you don't have to do one of these on the test.
All right.
It is a involved process, that is for sure.
Yeah, what's interesting is how ubiquitous it is. It just comes up all over the place. Not the detailed math, but doing Fourier transforms in one form or another just shows up in a lot of different areas.
When I had to do some for analytical mechanics, I was able to do it almost entirely in CoCalc, so I didn't have to do a huge
Right.
amount of super involved math, and what I was trying to transform wasn't nearly as complicated as this.
Yeah, well, you could do this kind of thing in CoCalc. That is probably the more sensible way to go about it these days. The challenge is getting out of CoCalc the kind of answer that you want. In other words, getting a simple expression for what happens to those coefficients as you increase m. I don't know what sort of answer it'll give you. I know sometimes those systems don't quite give you as nice and neat an answer as you might like, but
I think Mathematica has a specific function just for Fourier series.
oh, it probably does. Yeah, that wouldn't surprise me at all. Mm-hmm.
So that would be an easier way of doing it, I guess. So John, for the steps more, are we allowed to use Mathematica or CoCalc?
Oh yes, absolutely.
Okay.
Yeah. No, I want you to use any kind of resources, as long as they aren't other humans. That's just fine. That's sort of what I've gone to for all of these online courses. I just have to assume people will use the resources that are available to them. I just trust you won't be consulting, housemates or uncles and aunts or other people on the. That would be cheating, but looking things up or consulting your textbook, that sort of thing, there's nothing wrong with that. That's what I will assume. Yeah.
So John, is it going to be like a quiz format exam, or like we have an event that's open for a specific number of hours?
It will be very much like the first. Didn't we already do one like this? Well, let me see. When did we do our first
quiz?
test? You did a quiz. Okay.
We-
Yeah. Just imagine that expanded to, instead of one problem, like 4 or 5. And probably I would leave it open. Didn't we say it was tomorrow? So I'll just leave it open all day. And so you come in at 8 o'clock or whenever you feel like it and get started, and you just have to work at it all day long. And I think I'll have you submit submit your answer to each problem separately. So, take a picture of problem number 1 and submit that, and carry on in problem number 2, so that I'll have a picture of each one. That's
John,
how I did that successfully for general physics, and it worked pretty well. So
I was wondering if it would be simpler if you make it as like a homework assignment and it's open till midnight, and it's like, and we can just submit a PDF of the whole exam.
well, I'd rather not do that. I'd really rather have it in. It's easier to grade, to go from one to the next, if I don't have them in. It doesn't make that much difference, I guess, but it's what I've been doing. So I think I'll stick with just putting them in. It'll be in Moodle. It'll be like the Moodle quiz that you just took, and just have you take a picture of each one.
Is it gonna be like when you start it, you have like 3 hours to finish it, or is it just like work on it? Like you can do like morning for
I'm
afternoon?
with you guys. I think I'm inclined to say no. I'll just take the whole day, and so I probably the only thing you should watch out for. I'm trying to remember. I think I need to enable a time limit even if I don't really use it, so that there's some weird effect that if it reaches the final time limit, if it reaches the final time, the closing time, and there's not an enabled time limit, it closes it and doesn't even send what you've done. There's some weird thing like that. So I may put a time limit in it, but it'll be like an 8 or a 10-hour time limit or some such thing, so that it really won't limit you. What if I went from 8 to midnight? What would that be? 16 hours? I guess that's 16 hours. Okay, so I'll give you a 16-hour time limit. And I guess midnight makes sense. I'll probably back it up 1 minute, just because that's what you can do easily. It's a little hard to stick it right at midnight and not goof up the date and whatnot all. So probably 4 or 5 problems, and you'll just take a picture of each one. I don't think I'll try to do more than that. And they will be similar to the ones that you've just been looking at on this very, well, it could be. Some of them will be very similar to these, and there might be one or so others, 1 or 2 others that are from homework that you have done. But you shouldn't see, I don't plan to do anything new. So
are we expecting about 4 problems, like
4
our
or
last
5.
exam? Okay.
Yeah, 4 or 5 problems of this type. So let's take a look at the second Fourier transform problem. See what we can learn from that one. And then that's really all I have. So I think we can conclude after that. I got to change cameras here.
Haven't gone over the practice problems yet either.
The first 3.
Oh, that's true. We haven't gotten to those. Yeah, in fact, maybe we should do those first. Let's do those first and come back. Okay. Yeah, I forgot about those. So what was the first? Oh, the Michelson Interferometer. Yeah, did you have some fun with that?
We had some confusion with that.
Okay.
But it was fun. It was fun confusion.
Fun confusion. Oh, I love this terminology. Fun confusion. So I was using the ideal gas law to try to get my way through this.
John, you're showing us the second problem.
Actually, I'm not. The numbering is different.
Okay.
So what I did was I first worked out what kind of change was needed in n, in the index of refraction. So you've got some hot air region, and it's a 10-centimeter path, but you go through it twice. Let's see where I took that into account. Or it was a 5-centimeter path. 5-centimeter region. Okay, it's a 5-centimeter region, but you go through it twice, so that's 10 centimeters. And so I use this idea of optical path length as the index times the distance. And so the optical path length is this index 1.00029 times 10 centimeters, or a tenth of a meter. That gets me this optical path length for the other branch of the interferometer where it doesn't go through that. Now, to get a change, I just figured out what change was needed in n to get a shift. I want to shift it by 1 full wavelength. So I want to shift it by 633 nanometers. So I need a change in the optical path length of, this is just in meters now. And just taking the ratio of these two tells me how much n needs to change. That's where I got this number. Trying to think if that's right now. Let's try this again here. So the optical path length, let's say beam 1 and beam 2. This would just be n times L, or 1.00029 times 0.1, and that's 0.1000029. This would be n plus delta n times L. If we look for the difference between these two, it's just, okay, so the path difference is just going to be delta n times L, and I want that to equal lambda. So delta n has to equal lambda over L, which is exactly what I've got right there. Does this make a little more sense? So here's the optical path length in one beam, and here's the optical path length in the other beam where the index of refraction is changed by a little bit. It's got the original value plus some change. And then if we just say, but we want a difference in this optical path length to be lambda, the difference in the optical path length is just this delta L times L. The n times L would cancel out. So we just have delta n times L. Wanting that to be equal to lambda, then delta n has to be lambda over L. So that's what I found up here. So that's the change that I want in the index of refraction. That's a pretty small change. So if you look at that with this n equals 1.00029, and now we've got this 0.000 and 3 more zeros, and then 633. That's what we're talking. The change we want to happen is even beyond the 2 and the 9. So it's going to be a very small change indeed in the index of refraction to cause this effect. So then I said, well, if the index of refraction normally is 1.00029, which is like 1 plus this number, 29 times 10 to the minus 5, and assuming this just varies linearly with the density of the air, and then I started pulling out the ideal gas law and came to the conclusion that density times temperature is a constant. When the temperature goes up, the density goes down in such a way that those two are a constant, which I sort of proved by messing around with the ideal gas law. That's probably some named principle by somebody or other. I don't know. Somebody's law, surely. So I just wrote it as this factor 29 times a ratio of densities here. The actual density divided by sort of standard density. And then if you're at standard density, you've got this number. If you're at twice standard density, you'd have twice that much. That sort of thing. So that's where I'm just saying it's proportional to density, the change from 1, this 2,9 piece. Now that's doing it as a function of density, but we can change that to be a function of temperature instead. You have to flip it over because rho times T is a constant, so when rho goes up, T has to go down. So now I've got the standard temperature on top, and the particular temperature we're at is on the denominator instead. And I just put in 300 Kelvin for that. You have to put the temperature in Kelvin for this all to work. So 1 plus 29 times 10 to the minus 5 times 300 over T. That's what the change in index, or that's what the index for air would be. Then if you think, well, how is that changing from the standard value? That would just be with a, well, here yeah, what have I done? I guess you could say I took the derivative. Delta N with respect to t. And what I get is 1 over t squared times dt. It's a little bit what this is doing. It's one way of writing it anyhow. So the change in index now is 29, and here I've put in t is 300. Why didn't I square that? I should have squared it.
It's because there's the 300 on top.
Correct. Yes, exactly. Okay. Yeah, okay, so then it's this 29 divided by 300 times delta t. And that's where I put in all the numbers then, taking the needed change in the index down here is the thing that I had found earlier, and I put that in and came up with a delta t of 6 Kelvin or Celsius. It's a delta t, so those would be the same. So 6 degrees would give you a whole fringe. Which is why we can pretty easily see that. You know, with your hands, you could easily imagine creating a few degrees of change, and that gives you some fraction of a wavelength, and so you can see the fringes shifting around a bit. Here's a way of sort of graphically representing what I'm doing, that as density increases, I'm imagining that this index starts at 1 in a vacuum and goes up linearly. Does that all make sense? I feel like I'm losing you guys, but I don't know.
We're just tired.
Been up late.
I can understand when you explain it to us. I'm just not certain that I could make the jump of correlating the density, or how to correlate the density into index.
Yeah, well, this is the kind of thing I wish we would somehow teach more, because this is more like a real life problem where, you know, you think, well, how can we sort of approximate this and get a rough answer? And you have to kind of know how to set up linear relationships and use them and get your way through. And it's not easy to teach that. And you kind of have to go through things like this several times until you sort of recognize what's going to happen and even know, so that you don't, it's easy to make mistakes and you have no clue whether you're right or wrong going through something like this, but yeah. Let's move on. That was number 1 is what I called it when I gave it to you. 2 is the 5 slits. That should have been more familiar. We worked on that before. Here's my plot. Did you get something like this? Should have 3 little bumps in between the big ones. And This thing nails the n equals 3 main peak. And that's because of the 1:3 ratio of the spacing to the width. So that should knock off the third one. Then for the phasor diagrams, that gets a little dicey. The minimums you should be able to draw exactly. A pentagon and a 5-pointed star. Those would be these two minimums, and those are exact. The maxima, I think this one is the only one that is strictly correct. These others are kind of some weird figure that what is it, Ben? You were showing.
It'll be some oddly pointed star, probably.
What I'm wondering is whether it's a 6-pointed star, but we only see 5 of the points.
I don't see how it would become a 6-pointed star from what it's at right now.
Yeah, I don't know. Let's not spend a lot of time on that one. I don't think we're going to learn a lot. Yeah, they're going to look the same. Mine look rather different, but they should look essentially the same, just flipped somehow. And then, of course, you should have just a straight line of arrows for these peaks. Okay, well, was that?
If we labeled our x-axis with like 2/5 pi, 3/5 pi, 4/5 pi.
Oh, I don't care, as long as you do it in some consistent way and then tell me what the scale is.
Okay.
Yeah, you'd have to say this is scaled by whatever the width. You'd have the width in there somehow, wouldn't you? One of the widths. I'd like you to connect it so that somebody could figure out. Well, what did I say here? Oh, I just said label the horizontal scale with units. Okay, so that gives you a lot of leeway. I did it here in millimeters. Which I guess is why it doesn't come out to anything exact. Yeah, I just did a little calculation, so it came out in millimeters. I'd like you to be able to connect it with millimeters to a distance somehow. You know, if you want to label yours as pi or something, at least show the equation that would enable you to go from that scale to a distance.
And the distance would be the
distance on the screen,
okay.
Measuring along the pattern on the screen. So if you actually had a picture of the bright and dark fringes on the screen with a ruler on it, that you could correlate your peaks with the markings on the ruler. That's
Would
just
that not
really
be...
That's just a matter of the definition of beta and alpha in terms of A and B and K and pi, I think, is all you have to. You just have to put all that together.
Okay.
I don't have that here. I don't think. I didn't do it that way somehow. Hecht does kind of bury his definitions of alpha and beta at times. I wish he had a little bit more clear statement of those, but at least I believe alpha if I can find those. I always have to look a while to pull those out. Okay. I think this is Ka over 2 sine theta, and beta is Kb over 2 sine theta. And then you can also relate theta and y, and I don't know, what should we call it, r. And so tangent of theta is y over r. But in general, we equate tangent and theta and sine and theta. Sine of theta and tangent of theta are the same, essentially, for these small angles. But that gets you from a y on your figure all the way to the alpha or beta that you're using in the formula to calculate the intensity. It's several steps to get there. Yeah. Okay. Shall we move on? Oh, the satellite receiver. Yes, indeed. All right, I've got a zone size of the radius of 1.63 for R1 and 2.3 for R2 in millimeters. Wow, this is tiny.
We had the opposite thing. We ended up with meter size.
Really?
Multi-meter size.
One of
things.
us is
Yeah.
wrong. See if we can figure out who.
We kind of assumed that multiple meter sizes would be reasonable given that radio
Yeah,
waves are so large.
That makes a lot more sense than what I've got.
We had a very different wavelength than you have there.
Yeah, you sure did. Yeah, this is the wrong. Okay, this is not the right answer. What did you find? I thought I had done that one, but the trouble is I change these problems, and I thought I had a solution from an earlier test, but it looks like I don't.
For the first zone, we found a radius of 9 meters plus decimals. The second one, basically 13, and the third one, pretty much 16.
Here we go. No, okay, here I got something much smaller. We'll see if these numbers make any more sense.
This, of course, is all predicated on the fact that we calculated a wavelength of 16 meters.
Well, there I disagree with you.
Why is giga times 10 to the 9th there? Did we just use our wrong prefix?
Yeah, I think we assumed mega, not giga.
Oh, we went 10 to the 6th, not 10 to the 9th.
Okay, there you are, because what I've got is 0.016 or 0.017 meters.
Okay, and we won't even be a power of 10 off, or like a couple powers of 10 off because of the square rooting that is going on.
Yeah, so you're off 3 powers of 10. That means your answer will be off about a factor of 30. Square root of 1,000 is about 30. 316 if you want to know. But so I get something very reasonable actually out here for these different radii. So 30 times 30, what was your R1? It should have been about, golly.
About 9 meters.
Yeah, about 10. Okay, that makes kind of sense here. Because
all of the rest of the math looks like what we did. We just had the wrong.
Yeah, you just got the wrong number right in here.
Yep.
Okay. Okay. Well, then to construct this thing, you've got to build something sort of like this, clear foil, with these different radii. And what you hope to get then is a bright spot surrounded by these kind of weird rings. And then the question is, how large will that focal spot be? And there's a couple different ways of getting that. One way is just to say, well, this is kind of like a lens, and the diameter is the diameter of this outer zone. And just calculate it that way and use the usual 1.22 lambda over d. Then to get the actual size of the spot, you got to multiply by the focal length. 1.22 lambda over d would give you the angular size of what comes through, and then to get the linear size, you multiply by the focal length. And I got 10 centimeters.
In this case, the focal length being the distance.
The 5 meters.
Okay.
Yeah, that's just the 5 meters. How far away are you picking it up? It'd be fun to try to build this and see if it would actually work. I don't think it would be a particularly practical approach, but it could be fun to attempt anyhow. And yeah, I guess I didn't give you part D here, was what would you do to make a smaller spot if you wanted to make it focus to a tinier spot.
Could you just include the first zone?
That would make it worse.
Okay.
Add more zones to the exterior?
Yeah, you'd add another outer zone. The more zones you add, the finer the spot becomes. You know, though, yeah, that's right. If you think about it in terms of the way we've looked at this with an aperture, as you move an aperture, if you think your whole thing is, you wouldn't get very far off before you had shifted by one zone if you went out further in zones. Then those pictures we were drawing of as you move off center, you would be reaching the point where you've touched the next zone much sooner if you had more zones. So all right, well, where are we? Do you have other questions? Are we ready to just go for broke and see what happens? Well, this has not been the optics class I was hoping for. You folks have been fine. I'm just thinking in terms of not being able to do some of the stuff in the lab. So we'll have to see when this whole thing ends. I think it would be great to have somewhere down the line, maybe a year from now, you can all come and on an afternoon we'll just play in the lab some more and see some of the stuff that was very hard to try to show you with the computer camera, the webcam. So, but let's do a little bit more. We'll do this test, and then I'm eager to see where you're coming on your little presentations, and that will conclude everything, I guess.
John, we still haven't gone through 53.
We haven't what?
Problem 53 on chapter 7.
Oh, you want to look back at that? Okay, let's do that. Chapter 7, 53. That one is more a look at it and answer it kind of thing. Find it. Well, that's clear enough on my screen. I don't know how it is on yours, but so you're supposed to explain what's happening in the successive parts. First of all, just the general trend from the original functions, what's different from one to the next? We have to assume these continue. This is just the first few cycles and eventually just the first cycle, but assume these continue. What's changed from one to the next? Oh, Ben, let's start with you.
It looks like they're about twice as, each one lower is about twice as wide. And that is pretty clear, at least from, or I guess the duty cycle changes. And
Yeah, well, actually the duty cycle does not. The wavelength is changing.
yeah.
duty cycle is the percentage, and that's 50% in all of them. But the wavelength is changing. That's even written right here. It's got different wavelengths. And here it is a factor of 2. Here it's a factor of 3, I guess. So this is a function in x, and so we're looking at a wavelength. Over here, these are Fourier components, and what they represent then is spatial frequencies, if you like. That's what K is representing. I don't quite know why. Why does he have M times K? I don't understand what he means by that.
Wasn't that the same way we labeled our X graph in the Fourier transform that we did just earlier today? Our x-axis? Or no, we had k times x. Never mind.
Yeah, I'm confused by that labeling. That doesn't quite make sense to me. I'm just curious whether it's the same way in the earlier edition or whether an error has crept in here. Chapter 7. Oh, shoot. Now it's a brand new problem, so that doesn't help us. It didn't exist in the earlier edition, so that's no help. It just seems odd that you have a variable called mk whose value is k.
Those wouldn't be the values of m, like tagged onto the k, would they?
I guess he's just saying, it's k,
Maybe like for the
2k,
odd values of k.
3k, and 4k. But the question I have is, what scale is it on? I mean, obviously he's got it on some kind of a scale, because down here he puts k over further. Which is the right thing to do. K is smaller in this case. Where lambda gets bigger, k gets smaller. Yeah, I'm just a little confused. But in any case, this is a k-axis, whereas here you have an x-axis. And you would put distances in meters on the x-axis, and on the k-axis, things would be per meter, inverse meters of some kind. And in general, you would make this be an axis on which you would have, and the question might be, what per meter? And the usual answer is it's just radians per meter. So a 1 on here would be 1 radian per meter. But he's labeling them with the letter K as well, which just confuses me a little bit. I've got to think a little more about that. But how do you understand this very first peak? Right there, or here, or this real close one down here. Lucas, tell me what you can say about that peak. What is that indicating?
Well, if it's like the last one, then it just indicates that there's something there, but we don't have a value for it necessarily. Right.
Okay. So there is something there. In other words, this function has some of that in it. What is that it's representing?
Is that going to be the amplitude of the square wave?
Not of the square wave.
Is that the average amplitude, like A naught over 2?
Oh, no, I'm not talking about this one. I mean the first one, the number 1 peak. The A0 would be just the average of the function. If you just forget about the fact that it's changing, just average it over a big long time, that's where you get the A0 number. And you notice these all have the same average, and it's not 0. That's because they go between 1 and 0. They don't go between 1 and -1. They're not a symmetric function. So that's the reason that you get something in the A0 term.
So at A1, that would be like the first sine function, right?
Mm-hmm.
And so that would be implying that it's matching better than in some other places.
Yeah.
Or that would just be where the first sine function is, and however tall that is how much of the area it matches.
Yeah, the only thing I would quibble with you on is I believe the A is the cosine functions, actually.
Oh, yeah. Yep.
We're doing cosine functions with this one, and so that would correspond to the first cosine function. This would be, if you like, the 0th cosine function. And here's the first cosine function. And so that's a cosine function, and presumably since that's the first one, that's the one that corresponds with this wavelength. In other words, it would be a cosine with that same wavelength. Now, what about this dot at 2K all the way down here? Why is there a dot there? That suggests the value is 0.
Would be like exactly opposite to the function?
No, then you'd get a strong result. It would just be negative. Okay, I gotta get down here now. Okay. Here's our original function. Now, what does that A2 dot represent?
Is it when we've completed one full wavelength?
No, this would be, you just have to remember what function are we trying to integrate. We multiply a component, cosine or sine component, times this and then integrate. But what particular one are we looking at for the A2 coefficient? The A1 would be a cosine of the same wavelength. So here's A1. It looks sort of, no, it would look like this. Because that's the wavelength right there. So there's a cosine function with the same wavelength as the original one. And when you multiply these together and integrate, you don't get 0. You'll get 0 through here, and then look at all of this. You're going to be multiplying that, and you'll get a negative number, but you're going to get something. And then over here, you're going to get 0 again. So you'll certainly get something from that section right there.
Is it a one with half the wavelength?
It's got half this wavelength, exactly. Now, let's see if I can draw this. This is going to be a challenge. Now, what we care about is this region right here. This part of the function, because we multiply it by this function, and we'll get something through here. Out there, it'll be 0 again, so we don't care about it. So we're integrating just over this range right here. Do you see how we're going to get 0?
Mm-hmm.
We have to get 0 just by sort of symmetry of what's going on here. And by a similar token, if we did A4, I won't try to draw that, but we would get 0 again for A4. But not A3. I don't know if I can draw A3. I don't think I can. But you won't end up with symmetric pieces that you can cancel out. And so you'll get something for A3. But A4 will be 0 again, and A5 you'll get something. As you go higher and higher in frequency, you start to see, yeah, but you're going to get less and less and less. Through the middle of this section, you'll have a bunch of oscillations that will all cancel out, and you'll only be left with some little piece at each end that will count. And that piece keeps getting smaller and smaller. And so the terms, the individual terms, keep getting smaller as we go up. So that's why this one was 0. And with a little more reasoning, I think we can show that all the even ones are going to be 0. Notice we talked about how here we've changed in wavelength. So we've gotten a larger wavelength or a longer wavelength as we've gone down. What does that do over here? You see that it squishes things towards smaller numbers, so that you have, in a sense, this bar here represents a sine wave, but with fewer cycles per meter. Where over here you have meters per cycle. Here there are fewer cycles per meter. So it's shifted towards smaller numbers. If you went to time and frequency, you would say, okay, here's a longer wavelength, but you'd think of it as a lower frequency. And you can see that directly in the plot, that the K is a lower number, because those represent frequencies. They are spatial frequencies. They're not so many per second, it's so many per meter. It's a spatial periodicity or frequency. It's interesting, we're getting just the opposite sign here. I don't quite know how to explain that. If you look back at my A1, I would expect to have a big minus sign here because this is opposite to the original function. And he shows that as a positive number. I don't know what I'm doing wrong here. Somewhere we've got a minus sign problem in this analysis. So we've talked about why there are no even terms. I think we've already talked about why there's a DC term. He's using that in a funny way. Did you recognize this DC term? That's a funny use of the word DC. That just comes from alternating current or DC being direct current. And AC and DC basically are used not to mean current at all. It just means alternating or steady. That's how they're used, which is why people talk about a DC voltage. Well, how can you have a direct current voltage? That doesn't make any sense, but that's how it's used. So AC just means alternating, DC means steady. So you've got the DC term in this is just the A0. The A0 reflects the average level of the function. And so it's like if you filtered it down so that you only let through DC, that's what you'd get. If you only let through the steady value, it's going to average at whatever that is. So that's what he means by the DC term. So you can call this this first bar, it's the average of the function, or the DC term, as opposed to all of these others that are frequencies of some kind. This one has a zero frequency. All right, let's say that's done. How about? And move on and be ready for a test tomorrow. I'll try to give you one that I think you can do, and hope that you don't spend too long at it. I don't know, some hours maybe, 2 or 3, something like that. But I hope you don't spend 6 or 8. But yeah, okay. And then I guess we meet again on Friday, 2 o'clock, and we'll talk about your presentation topics and such at that point.
John, are you going to put this video on Moodle along with all the solutions?
Oh, the solutions. Okay. Yeah. It takes a bit of work. I have to go through, see if I can find them all. I will try. Okay. I guess that's all. We'll see you on Friday.